Hi, my name is Sajid Mustahim. In this video, I'm going to talk about multi-phase fluid flow modeling in porous media, more specifically two-phase fluid flow modeling. But if you learn how to model two-phase fluid flow, you'll also be able to easily model three-phase fluid flow, and if you want any more number of phases that you want. All right. I've divided this video into three parts. In the first part, I'm going to talk about two-phase fluid flow modeling in porous media, but I'm going to consider that there's no pressure discontinuity between the two phases. In other words, the capillary pressure is zero, all right? So in this case, we don't have two different pressures for the phases, all right? So the number of equations and also the number of unknowns is one less than the case that there are two different pressures. All right, great. In the next part, which is the second part, I'll talk about two-phase fluid flow modeling, but I'm going to consider the effect of capillary pressure. All right, and in the third part, I'll model two-phase fluid flow in a fractured porous medium. All right, so let's get started. I'm not going to get into the details in this video, and I'll just talk about the things that are related to multi-phase fluid flow modeling because in the previous video, which was about single-phase fluid flow modeling, I talked about many of the sections that are written here, and so I'm not going to talk about them in detail. And if you watch that video, you'll understand what is going on in those sections of the code. In this section, we define the domain and discretize it. And I have defined and I have specified the number of cells in each direction of the model. And here I have specified the lengths of the model in each direction, and use the function cardGrid in order to actually extract the information of the domain that I have, the discretized domain that I have. Great, and I've used the function compute geometry in order to receive additional information about the structure that I have, and I'll use those pieces of information in order to model what I want to model. All right. In this section, I have defined the properties of the rock, and in this section, I have defined the properties of the fluids that I have. But in the case of single-phase fluid flow, I defined only the properties of a single phase. But here, it's obvious that I need to specify the properties of two phases. There's also another difference here. For specifying the properties of each of these phases, I've also specified another property, which is the relative permeability of each phase. And as you see, I've used this function in order to define the relative permeability of water, and used this function to define the relative permeability or to model the relative permeability of oil. All right, but you can use the function that you think works better for your model. All right, great. So let's take a look at the relative permeability curves that I have based on the functions that I defined here. Let's run the code to this line. I just did it. And now we can see what the relative permeability curves look like. And as you see, this is the rel perm curves that I have. And this is the relative permeability curve for water, and this is for oil. All right. In this block of the code, I have actually determined the properties of the wells that I have, and I'm not going to talk about them because I talked about them in the previous video. Here I have specified the bottom hole pressure for the production well and specified the injection rate for the injection well. In this section of the code, I have tried to actually calculate the initial pressure in the reservoir. In the case, actually, as we move in the vertical direction, pressure changes. In other words, I have considered the effect of gravity on the pressure, here. All right. Of course, in the previous video, I calculated the pressure using another method, but here I have used this method in order to calculate the initial pressure distribution in the reservoir. All right. Here I have computed the half transmissibility first, and then transmissibility of the interior faces, or at the interior faces of the model. Here I have gotten the discrete differential operators that I need to use in order to write the equations that I have, all right, which in this case is actually pressure equations. Here I have used the function init variables ADI. Why I have used this function? Because I'm going to use automatic differentiation when using Newton-Raphson method. All right, I need to use the Newton-Raphson method in order to solve the set of nonlinear problems, nonlinear equations that I have. All right, and the first input argument of this function is the initial pressure of the reservoir or the porous medium that I have, and the second actually input argument which this function takes is the initial water saturation. All right, these are actually the unknowns of the model. But you might be wondering why don't we have oil saturation as the unknown of the model? Because I have already substituted actually the constraint relation for saturation in the pressure equation. All right, so when I substitute that equation in the pressure equation, the number of unknowns decreases to actually one less unknown. All right, so that's why I don't have the oil saturation as an unknown here, and I don't have two pressures as the unknowns because I considered that the capillary pressure is equal to 0. All right, so I only have two unknowns for this system. Great. And here I have specified some numerical some properties for numerically solving the system. The total number of time steps is 50. The total simulation time is 100 days. And here I have calculated each time step size. And as you see, I have considered that all the time steps have the same size, all right? And the tolerance is this, and the maximum iteration is set to 10. So if the number of iterations in the Newton-Raphson method exceeds this value, we would say that actually the solution actually did not converge, and so we don't have any solution to the problem. Or maybe there is a problem with the code that you have written, or maybe you need to reduce the time step size in order to converge, or do something like that. All right. Or you can also actually increase the grid size of your model. All right. This is another thing that may help your model converge. Great. Here I talked about these in the previous video. I'm not going to talk about them. And here the main loop starts. The first iteration of this loop calculates the solution to the first time step of the model, and this is the end of the main loop that I have. And when the first iteration is completed, if the number of internal iterations for the Newton-Raphson method did not exceed that value, which was 10, if that number doesn't exceed, we get a solution to the problem. All right, but if that number exceeds, we say that the problem, or the solution did not converge. All right, and if the solution converged, and we will store the results of the first time step in this struct. All right, and after that we will go to the second time step. All right, great. And inside this main loop, there is this interior loop which is for the Newton-Raphson method, and this while loop helps us find the solution for each time step of the problem. All right, and I have written actually the governing equations that I have inside this loop, which you see here. This I have named this the water equation, and I've named this the oil equation. All right, these are actually pressure equations. In the previous video, I named them pressure equations. These are pressure equations. This is the pressure equation for water, and this is the pressure equation for oil. All right. At the beginning of this interior while loop, I have updated the densities of the fluid. As you see, I have updated the densities, and here I have updated the pore volume of each cell in terms of the pressure that I have. Here I have actually calculated the mobility of water and the mobility of oil, and here I have calculated the pressure gradient, and here the gradient of length, I could say, or the difference between the positions of actually the centroids of the cells. All right, here I have actually calculate the pressure gradient, also considering the effect of gravity. All right, And here I have calculated the water flow rate and the oil flow rate, which is actually the Darcy equation. All right, you already know that. I've used the Darcy equation to calculate the water flow rate and the oil flow rate. And as you see, this is the density. Density is multiplied by mobility of water. The density of water is multiplied by mobility of water times transmissibility times pressure gradient. And as you see, I have used the upwind scheme in order to get the multiplication of these variables. All right, when we have advection, we need to use the upwind scheme in order to get these properties. Here using the properties that we previously calculated, now we have written the governing equations that we have. The water pressure equation, the oil pressure equation. This is the accumulation term of the water pressure equation, and this is actually the flux term for the water pressure equation. Here is the accumulation term for the oil pressure equation, and here is the flux term for the oil pressure equation using the divergence operator. All right, great. And in this part, I have added the boundary conditions to the governing equations that I have, which are actually the source and sink terms. All right. As you see, this is the pressure equation for the injection cell. The injection cell index was determined here, which is actually, let me run the code to this line to see what the index is. As you see, the injection cell is 1. The injection cell index is 1, and the production cell index is the last cell of the model. Let's see what numbers they are. This is 1, and this is the last cell. We have a total number of 100 cells in the model, as you see. And so the last cell of the model has an index of 100. So let's go to this line, which we were talking about, and we were going to add this term to the water pressure equation for the injection cell. And as you see, I have multiplied the injection flow rate by the density of water. And here I have calculated the production flow rate. As you know, we set the bottom hole pressure, so we don't know what the flow rate is for the production well. So we need to calculate the production rate, and I have done this here. And here I have added this value to I'm sorry. Of course, here I have not used it. If I uncomment this line, you'll see that I have used this flow rate here. And because I have already multiplied the density of oil here, I no longer need to multiply the density. by this value here, because it is already multiplied and its effect is considered. But here, the density was not considered previously, and so I needed to multiply this volumetric flow rate by the density of water. All right? Great. But as you see, there are two methods in order to specify the boundary condition for the production well. Because I have the bottom hole pressure for the production well, I'm also able to actually specify the boundary condition using the bottom hole pressure of the production well. But in this case, I need to subtract this value from the pressure of the cell in which the production well is located. All right? And as you see, this is exactly what I said. All right? Great. So there's no difference, which of these, methods you use. All right? Actually, and great. And here I have, specified the boundary condition for the water pressure equation, but here I have used the water saturation to set the boundary condition. All right? But this is not a source and sink term at all. All right? This is a source and sink term, but this is not. This is not. These are boundary conditions. Better to say that they're boundary conditions. Great. And here I have specified, the boundary condition for the water pressure equation. But for the production cell, I've used the water saturation to do that. I have subtracted the initial water saturation actually of the initial water saturation of the model. I've subtracted the initial water saturation of the model from actually the water saturation of the cell in which the production cell is located. All right? Great. So in this way, I specify the boundary conditions, and now it's time to actually concatenate the equations that we actually wrote. The equations consist of these two equations, and here we get the Jacobian and the values and the increment here, and using the increments that we calculate here, update actually the pressure values and the saturation values. All right, and we use these updated values for the next iteration if the problem is not actually converged yet. All right, that's a very important point. And that's it. Here the loop is completed, and if, as I told you, if actually the residuals, if the residual is not less than the tolerance that we set here, what is the tolerance? This is a tolerance. If the residual of the equations is not less than the tolerance, we say that actually the problem did not converge, and we need to solve the problem again in order to get the exact solution. Of course, in here we don't actually get exact solution, but we try to be as close as possible. All right, and here after if the solution is converged, actually the values will be stored in the struct, and that's it. And here the outer loop is completed. Alright, so let's run the code to see what the output is going to look like. Alright, because actually, because the video recorder is running, it's being very slow, but there's no problem. Alright, so let's see what the output looks like. As you see, these are the three-dimensional outputs of the model, but because it's taking a lot of energy of the laptop, it didn't give me very good results. So let's run this last section of the code again. The results are already stored in struct, so I only need to run this last section of the code to see what the output looks like. Alright, and as you see, the water is being injected in, through the injection well in the first cell of the model, and as it is clear, the pressure is increasing on this side of the model, and the water saturation is increasing here, sweeping the oil toward the production well. All right. This is what I was going to talk about in the case of no capillary pressure. All right. That's it. All right. So let's stop it and let's go to the next section, to next part of the video, and I'm going to talk about this script. In this script, I have considered the effect of capillary pressure. In other words, each phase in this model has a different pressure, all right? But in the previous code, I considered that both phases have the same pressure, all right? Great, but here I consider the capillary pressure, and so we have two different pressures. In other words, we have two different unknowns. So we need to have one more equation. What is that equation? That's the pressure, the capillary pressure relation, all right? Which is actually the non-wetting phase pressure minus the wetting phase pressure equal to capillary pressure. Here, the non-wetting phase is oil and the wetting phase is water. So actually, oil pressure, actually the capillary pressure relation is oil pressure minus water pressure equals capillary pressure. Great. So these sections of the code are the same as the previous one, so I'm not going to talk about them. And as you see here, let's talk about those parts that are different from the previous code. And alright, as you see, I still have two parameters here. The initial pressure and actually the water saturation. But why the number of unknowns hasn't increased? Because I have already substituted the capillary pressure relation into the governing equations that I have. And let me tell you what I have done. As you see, we have here the oil pressure, and the water pressure is calculated using this relation. All right? Great. And here we have, the oil pressure. As you see here, I have, calculated the oil pressure gradient, the water pressure gradient. So, we have actually two different, pressure gradients. Did we have those in the previous code? Let's talk about it. Yeah, we had them. Why? Because actually the pressure gradient is different because of the difference in density of the two phases. All right? So I have considered them. But this pressure gradient is the same for both of the phases. All right? Wonderful. But as you see, this pressure gradient is different in this case, and also actually, in this case, which is the pressure gradient due to gravity. All right. And here I have calculated the water flow rate and the oil flow rate, and here I have written the water pressure equation and the oil pressure equation. And as you see, like the previous code, I have already substituted the saturation constraint into the governing equations. This is actually the oil saturation, but I have written the equivalent one, which is -1 water saturation. All right, and this is the same. 1 minus water saturation equals actually oil saturation. Why do I need to use oil saturation here? Because this is the oil equation, and I need to use the oil saturation in this equation. All right, like this. I've used the oil density. All right, here I have used the oil density. Here I have used the oil flow rate, and like them, I need to use the oil saturation here. But I've not written SO. I've not written SO. What I have done here is to use the saturation constraint, and I have written 1 minus SW, which is the water saturation. All right, this is what I have done, and I have done the same in this case. And the boundary conditions are almost the same, as you see, and that's it. This is the case for actually for when the capillary pressure is considered, and these parts are the same. I'm not going to talk about them again, and let's run this code. All right, and as you see, in this case, the capillary pressure is considered. This is the water saturation, and this is probably the oil saturation. Let's see, what it is. It is that this is water saturation and pressure. Pressure. Let's see what phase it is. All right. This is actually the oil pressure. As you see, I have stored the oil pressure in this struct. All right. So these are the parameters they have stored: the water saturation, the oil pressure, and the simulation time. Alright, and this is the output that you see. Alright, that's it. That's the end of this part. And let's go to the third part of this video, which is to talk about multi-phase fluid flow modeling in a fractured porous medium. And I'm not going to talk about three-phase fluid flow modeling anymore, because in that case you only the number of unknowns increases, and the number of governing equations increases as well. And in that case, instead of having two pressure equations, we'll need to have three pressure equations. All right, and in that case, we'll have, if you want to consider the effect of capillary pressure, in that case we'll have two capillary pressure relations. All right. So let's see, what is here in order to model multi-phase fluid flow modeling in a fractured porous medium. The only thing that you need to do in order to model multi-phase or single-phase fluid flow in porous media is that you need to change the properties of the rock. All right, but I'm going to use the equivalent continuum model in order to model the fractures, which is the simplest type of fracture model. All right, I'll probably talk about some other interesting fracture models in the future, such as discrete fracture matrix model, and also embedded discrete fracture matrix model, which are very, very interesting fracture models, and actually are more complex than this case, which is the simplest type of fracture model. All right, so as I said, I'm going to use the continuum, the equivalent continuum model to model the fractures. And in this model, I just need to consider those cells that are fractures to have a porosity equal to 1, and to have a permeability, a very high permeability. All right, great. What I'm going to do here is to use actually the structure, or the domain, which is already used in MRST, and it's actually in the geothermal module of MRST. And I have loaded this set of information, this set of data of the structure here, and because it's a very big model, it's a very big domain, it's actually three-dimensional. I have removed all the layers, cells of all the layers of the domain except one of them, except one of the layers. All right, so the model that I have here is two-dimensional in order to reduce the computational time. And in order to show you what the grid looks like, of course, I talked about this in the video about single-phase fluid flow modeling. Well, let's do it again if it's your first time actually watching this series of videos. And as you see, this is our model, which is two-dimensional. It's not discretized in the x and y directions. I'm sorry, it's discretized in the x and y directions, but it's not discretized in the z direction. and so it's a two-dimensional model. Great, and these are actually, you can see, the fractures of the model, and these are the fractures whose porosity and permeability are very high. The porosity is equal to 1, and they've got a very high permeability, which you can see their permeability in this struct. All right, if you open it, you'll be able to. I'm sorry, you'll be. Yeah, the properties of the rock are here. The amount of porosity for each cell is here, and the amount of, as you see, the porosities of these cells are 1, which represent the fractures, and these are permeabilities of the cells. Great. And that's it. That was the only difference between the two-phase, or it's better to say the non-fractured code and the fracture code. The other sections are exactly the same thing. All right, so let's continue running the code and see what the output of the fractured model is going to look like. Because the number of cells in this case is higher than the previous case, the simulation or the runtime, that's better, the runtime is more, and when the video recorder is not running, it's much faster. All right, so if you write the code yourself and run it on your computer, it'll be run and it'll be executed much faster. Great, so let's see the result. All right, the water is injected through this cell. All right, we encountered a problem again. Let's stop it and run the last section of the code again to see those axes more beautifully. And here they are. All right, the water is being injected into this cell and produced, and oil is being produced from this cell, and this is the pressure distribution in the reservoir, and this is actually the saturation distribution in the reservoir. All right, great. That was the whole thing I was going to talk about, and let me make sure that I talked about all the things that I was going to talk about. Yeah, that's it. I think I did everything I needed to do, and I hope you learned something. Thank you everybody for being with me, and hope you're having a great day.